This 18-ton open-die forging hammer shapes valve bodies for petroleum pipelines, delivering 630 kilojoules of energy without transmitting vibration to the ground. In the heart of maritime engineering, precision isn't just a goal, it's a necessity. Today, we follow the full process of overhauling a piston in a megacoulomb per megacoulomb sea engine, ensuring reliable performance on the high seas. The process begins by opening the crankcase door to access the crosshead and the piston rod stuffing box. The crosshead is turned downward, allowing access to the stuffing box and piston rod screws. The stuffing box is released by removing its innermost screws. Two distance pieces are mounted onto the piston rod foot to protect the lower scraper ring and guide the stuffing box safely during disassembly. The engine is locked out and tagged before the procedure begins, following safety protocols. All dismantled components are cataloged and tagged for traceability and proper orientation during reassembly. Next, the cylinder cover is removed, following standard procedure. A scratch mark is made on the liner and piston cleaning ring to ensure proper reassembly. The piston cleaning ring is then dismounted. At the top of the cylinder liner, wear ridges are carefully removed to prevent damage during piston removal. Special care is taken to maintain surface integrity of the liner, as scoring can lead to blow-by and decreased engine efficiency. Carbon deposits are also scraped off to prevent debris from entering the crankcase. The crosshead is then brought to top dead center, releasing the piston crown from the liner. A lifting tool is attached, and the piston is lifted straight out. The lifting rig is calibrated to handle the piston's weight distribution, preventing tilting that could result in liner contact. The lifting path is aligned to avoid contact with internal liner surfaces. The piston rod foot and the stuffing box are then lowered through the platform. Two support halves are installed around the piston rod and secured with screws. The piston is placed onto this support, and the lifting tool is removed. Rubber padding is placed under the piston to absorb impact and prevent surface damage. All surfaces are immediately wiped clean of any oil residues to prevent contamination during inspection. Before disassembling, the ring gap of each piston ring is measured. Using a ring expander, the rings are removed, cleaned, and inspected. The radial width of each ring is measured and noted, in accordance with the manufacturer's manual. The piston crown is thoroughly cleaned, and the ring grooves are inspected. The maximum vertical groove wear is checked, ensuring it stays within allowed limits. The burnway is verified using a template. Ring groove clearance is also verified with feeler gauges to assess potential blow-by risks. If wear limits are exceeded, the part is marked for replacement according to Class Society regulations. All measurements are recorded in the engine log for future maintenance tracking. Piston rings are installed with their top mark facing up, and gaps are offset by 180 degrees. The piston is lifted once more, and its rod foot is rested on a wooden plank. The piston crown is then landed on a wooden plank for safe removal of the lifting tool. During reinstallation, each ring's orientation is checked again manually to confirm proper seating within the grooves. Care is taken to ensure the rings remain compressed during insertion to avoid chipping. A lifting bracket is attached to the bottom of the piston rod foot, and the crane lifts the rod vertically. The locking wire and inner screws between the rod and crown are removed. Next, the piston rod is detached, and screws in the piston skirt are removed. Eye bolts are fitted into designated holes, and the skirt is lifted off. All piston parts are cleaned and inspected for wear or damage. Particular attention is paid to micro cracks, which are detected using dye-penetrant testing. The piston pin bearing surface is also measured for out-of-round or taper deviations. New sealing rings are mounted on the piston skirt and rod, each coated with lubricating oil. Guide screws are installed in the piston crown to ensure precise reassembly. The piston rod is installed into the crown, and screws are coated with molybdenum disulfide before tightening. Screws are tightened in a diagonal sequence and secured with locking wire, following engine procedure. Thread locking compound may be applied on specific bolts, depending on the engine maker's instructions. Lubricating oil is filled into the piston and rod assembly. A pressure testing tool is mounted around the piston rod base, and the unit is tested at the specified pressure. Contact surfaces are checked for leaks. After confirming tightness, the pressure is released and the testing tool removed. If pressure loss is detected, the component is isolated and retested after inspection. The stuffing box is mounted again. The lifting tool is fixed to the piston crown, and the support bracket is removed. The piston rod is cleaned and lubricated before insertion. Alignment pins, help guide the stuffing box into place to prevent thread cross-binding. A guide ring is fitted to the top of the cylinder liner. The piston is lowered into the liner, while the rings are lubricated. The rod foot is guided through the stuffing box and landed on the crosshead. The lifting tool and guide ring are removed. All movement is closely monitored to prevent misalignment, which could damage the liner surface. To complete the process, the top of the piston is coated with lubricating oil. The piston is turned downward. Distance pieces are removed, and the stuffing box screws are tightened to the specified torque. The piston rod screws are tightened and secured with locking wire. The piston cleaning ring is reinstalled in line with the original markings. Finally, the cylinder cover is remounted, completing the overhaul. A final hand rotation of the crankshaft ensures smooth operation before engine restart. Through every step, strict adherence to procedure ensures the piston is restored to full working order. This overhaul reflects the level of craftsmanship and technical mastery essential for safe and efficient marine propulsion. Every component, every measurement, and every turn of the tool contributes to a system built to endure the unforgiving ocean. In this environment, precision engineering is more than a discipline, it's a safeguard for lives and cargo across the globe. Laser metal deposition, LMD, is transforming how aerospace components are built. In this EU-funded project, engineers at TWI are developing a 5-axis LMD process to reduce production time for aero engine casings. The process begins with a focused high-power laser beam that generates a melt pool on the workpiece surface. Simultaneously, metal powder is fed through a coaxial nozzle into this pool, forming a weld track as the laser and nozzle move together. This additive approach allows new layers to be built with exceptional precision and customized properties. By stacking multiple layers, complex 3D geometries take shape directly from digital models, without the need for traditional casting or machining. The 5-axis movement offers greater flexibility, enabling deposition on curved and angled surfaces. This method not only minimizes material waste, but also enhances design freedom, making it a promising alternative for manufacturing high-performance metal parts in aerospace and other demanding industries. In this facility, circular saw blades undergo a multi-stage precision finishing process to meet high-performance cutting standards. The workflow begins with honing, which smooths the blade's surface and enhances flatness. Next, chamfering is applied using a unique alternating Chidori pattern that reduces edge wear and improves blade entry into the material. After that, wet grinding is used for side face processing, where fine abrasive belts remove material under continuous coolant flow to minimize heat distortion. This step ensures dimensional accuracy and prolongs the blade's lifespan. Then, a tooth setting machine engages. Twin units on either side push each tooth slightly to alternate directions, left, right, left, forming a staggered profile critical for smooth, efficient cutting. The process also includes fine band wet grinding, where narrow abrasive belts move automatically under controlled pressure and coolant, producing smooth and accurate finishes on narrow surfaces. In some cases, welded joints on the blade are also processed to achieve structural uniformity and functional reliability. These techniques collectively result in durable blades with consistent cutting geometry. By focusing on material removal accuracy, thermal control, and surface consistency, the operation maintains strict quality across every blade. In this facility, circular saw blades undergo a multi-stage precision finishing process to meet high-performance cutting standards. The workflow begins with honing, which smooths the blade's surface and enhances flatness. Next, chamfering is applied using a unique alternating Chidori pattern that reduces edge wear and improves blade entry into the material. After that, wet grinding is used for side face processing, where fine abrasive belts remove material under continuous coolant flow to minimize heat distortion. This step ensures dimensional accuracy and prolongs the blade's lifespan. Then, a tooth setting machine engages. Twin units on either side push each tooth slightly to alternate directions, left, right, left, forming a staggered profile critical for smooth, efficient cutting. The process also includes fine band wet grinding, where narrow abrasive belts move automatically under controlled pressure and coolant, producing smooth and accurate finishes on narrow surfaces. In some cases, welded joints on the blade are also processed to achieve structural uniformity and functional reliability. These techniques collectively result in durable blades with consistent cutting geometry. By focusing on material removal accuracy, thermal control, and surface consistency, the operation maintains strict quality across every blade. Watch the intricate process of dismantling, machining, and reassembling a giant gear assembly. The team carefully inspects and removes the worn components before using specialized machinery to restore and enhance each part's functionality. Once all adjustments are made, the assembly is thoroughly reassembled and thoroughly tested for precision. Finally, it's packaged and sent back to the customer, ensuring it meets the highest standards for performance and durability. The Sandvik grade GC 2220 turning insert is showcased in action, optimized for stainless steel machining. The process begins with rough turning and facing using the CNMG 1204 12MR 2220 insert. With a cutting speed of 180 meters per minute, 590 foot per minute, and a depth of cut of 3 millimeters, 0.118 inches. This insert handles initial material removal effectively. Next, finish turning and facing are performed with the CNMG 120408M MM 2220 insert, operating at 200 meters per minute, 656 foot per minute, for a precise surface finish. The insert's durability ensures consistent performance throughout the machining process. Finally, the bore is finished after pre-drilling to 40 millimeters, ensuring a clean, accurate hole. The entire process demonstrates the efficiency and precision of this dedicated insert for stainless steel applications. In this video, we observe the machining process of a complex component using a multitasking turning and milling system developed by Nakamura Tome. This machine is designed for highly efficient helical processing, enabling a variety of operations to be completed in one continuous cycle without transferring the workpiece between multiple machines. The process starts with feeding a round bar stock into the machine. The material, often stainless steel such as SO3303, is automatically loaded through a bar feeder. The machine is equipped with twin spindles and dual turrets, allowing for simultaneous operations on both ends of the workpiece. The spindles securely clamp the bar while it rotates, and the turrets move independently to perform a sequence of machining tasks. Initial rough turning is performed to define the general outer profile. Simultaneously, deep drilling is executed on the opposite end. As the process continues, contour milling, slotting, and grooving are carried out with high-speed rotary tools mounted on both turrets. Each turret is fitted with a live tooling system, delivering rotational speeds of up to 6,000 revolutions per minute. The upper turret is powered by a 5.5 kilowatts drive, while the lower turret runs on a 3.7 kilowatts motor. This dual turret approach reduces idle time and boosts productivity by overlapping operations. One critical feature of this machine is the Y-axis capability on the upper turret, providing a 70mm stroke. This enables the system to handle off-center machining, such as keyways, helical grooves, and angled contours, directly on the same setup. It eliminates the need for secondary fixtures or dedicated milling stations, which traditionally increase production time and the risk of dimensional error. Throughout the machining cycle, the system performs both external and internal operations. The twin spindle setup allows the part to be automatically transferred from the main spindle to the subspindle, which then continues operations on the opposite end of the workpiece. This handoff is seamless and precise, ensuring concentricity and alignment across all dimensions. Helical processing, the core of this machine's capability, is implemented by synchronizing spindle rotation with axial and radial tool movement. This allows threads or spiral channels to be created with high geometric consistency. Advanced feed control and real-time toolpath adjustments are used to optimize surface finish and dimensional tolerance. Following the helical and milling operations, the machine proceeds with chamfering and edge deburring. These finishing processes are essential for removing burrs, sharp edges, or tool marks that can affect part performance in assembly. The system carries out these tasks using dedicated tools mounted in both turrets, maintaining close tolerances and a smooth surface quality. Once all machining steps are completed, the part is separated from the bar using a parting tool. The subspindle then retracts, and the finished component is transferred to an unloading system or conveyor. Depending on the production setup, optional automation modules, such as gantry robots, shaft loaders, and unloaders, can handle the finished parts, preparing the machine to accept the next bar without manual assistance. Thermal control plays an essential role during long production runs. Integrated sensors continuously monitor internal temperature changes caused by spindle rotation, tool friction, and motor load. These readings are used by a compensation algorithm to make micro-adjustments to positioning and feed rates, preserving dimensional stability over time. This is especially important when dealing with tight tolerances or hard-to-machine materials. The system's spindle capacity supports bars up to 51 mm in diameter, with optional expansion to 65 mm. It accommodates a machining envelope of up to 190 mm in diameter, offering flexibility for various part geometries. The main chuck size is 8 inches, with spindle speeds ranging from 4,500 to 5,000 RPM depending on material and tooling. Programming and control are managed via a digital control unit featuring a user-friendly touchscreen interface. Machinists can load G-code, modify parameters, and simulate operations before execution. This reduces errors, shortens setup times, and enables easy transitions between part types. The machine is designed to support continuous operation with minimal downtime. Its robust construction allows for sustained use in high-demand environments such as automotive, aerospace, and general industrial manufacturing. Preventative maintenance is streamlined through onboard diagnostics, while data logging systems capture operational metrics for quality control and production tracking. Another advantage of this setup is its ability to eliminate secondary processes. Traditionally, parts requiring helical features, complex contours, and fine finishing would have to be transferred between multiple machines, lathes, mills, deburring stations, introducing risk and requiring extra manpower. With this system, all machining tasks are centralized, ensuring tighter process control, higher repeatability, and reduced handling time. Deburring, one of the most time-consuming manual tasks in conventional manufacturing, is fully automated in this process. The system applies deburring tools with precise force and positioning, ensuring uniform surface quality across the batch. It also improves worker safety by minimizing the need for manual grinding or hand finishing. In terms of layout, the system is built with a compact footprint, making it suitable for facilities with limited floor space. Despite its small size, the machine integrates multiple machining capabilities: turning, milling, drilling, part transfer, and finishing into a single unit, improving overall equipment efficiency. By combining high-speed tool movement, synchronized spindles, and real-time thermal compensation, this multitasking platform delivers consistent results over extended production cycles. Its automated workflow and integrated control allow manufacturers to scale operations without sacrificing quality. Overall, this production system illustrates the ongoing shift toward consolidated, high-precision machining solutions. In the rugged world of heavy lifting, wire rope splicing is where strength meets precision. At Tri-State Wire Rope in Salt Lake City, veteran riggers Rafael and Javier take on a 1-1/2-inch steel cable. Thick, heavy, and built for extreme loads in construction, mining, and marine operations. The process starts with precisely aligning the thimble into the eye of the rope. The thimble protects the rope from wear and distortion under load. The bright orange master link is attached, providing a secure connection point for lifting hooks or shackles. To prepare the connection, they trim one end of the cable and shave off part of the opposite side, making it easier to slide a metal sleeve over the splice. Using a hammer, they drive the sleeve into position, pressing it flush against the curved section to hold everything tight. This splice not only strengthens the rope's terminal end, but also ensures long-term reliability in demanding field conditions. Every hammer strike is calculated, not just to fit, but to forge integrity into the rope structure. The entire process requires both strength and precision, as each move must be exact to maintain the rope's load-bearing capacity. Proper splicing is critical for safety, especially when working with cables this size. Each step reflects a blend of force, technique, and understanding of materials. The production of high-strength bolts and nuts begins with selecting the right materials. Raw metal stock is carefully heated to specific temperatures, making it malleable for the next step. The material is then fed into specialized machines that shape and thread the bolts or nuts, each machine calibrated to ensure the correct dimensions. This process is followed by an inspection to check for any surface defects or inconsistencies. The machines also ensure that each part meets the exact specifications needed for its intended application. After shaping and threading, the components are placed into a series of finishing processes. These steps include cleaning, deburring, and coating the parts to enhance durability and resistance to wear. Each piece undergoes rigorous testing, such as load-bearing and corrosion resistance tests, to ensure it can withstand extreme conditions. The final products are then packaged and ready for use in industries that demand reliability and strength. Massive rings like these start with extreme heat and force. To create a forged ring, a solid metal billet, often steel or titanium alloy, is first heated until glowing red. Then, it's pierced and expanded using ring rolling machines to reach precise outer and inner diameters. The largest example, a 15.673-meter stainless steel ring, holds a Guinness World Record. Other parts, like magnetic yoke rings, require precise shaping to ASTM A668K standards and weigh up to 160 tons. Each forging is heat-treated and tested for structural integrity before use in energy, mining, or heavy industry applications. This complete brass forging line demonstrates how raw material is transformed into high-quality forged parts through a series of integrated processes. The line begins with the sawing station, where long brass rods are automatically cut into billets. Each billet must meet exact length requirements to ensure uniform heating and reduce material waste during forging. Once cut, the billets are conveyed to the graphitizing machine. This stage applies a thin graphite coating that serves two purposes: lubrication and anti-adhesion. It prevents the brass from sticking to the die and reduces wear on tooling, crucial for high-volume production. The coating is applied uniformly using rotating nozzles or rollers, ensuring complete coverage of each billet. A brief drying phase follows to allow the graphite layer to adhere before entering the furnace. The coated billets are then sent into a reheating furnace. This induction or gas-fired furnace heats the billets evenly to forging temperatures, typically around 700 to 750 degrees Celsius. Uniform heat distribution is vital for consistent deformation and structural integrity. Temperature sensors and programmable logic controllers monitor every billet's thermal profile to maintain process stability. Any billet that doesn't reach the target temperature is automatically rejected or rerouted. At the heart of the line is the eccentric mechanical forging press. As billets exit the furnace, they are immediately fed into the press. High-speed strokes form the billet into its final shape within a closed die system. The press ensures high repeatability, force, and precision with each cycle. Sensors at the die cavity monitor stroke depth and tonnage in real time to prevent overpressing or tool damage. Forging cycles are optimized to balance deformation speed with die life. After forging, hot parts are ejected and collected on a conveyor. Depending on the downstream setup, they may proceed to trimming, cooling, or cleaning stations. Throughout the process, automation plays a key role. From sawing to pressing, material handling is fully synchronized to maximize throughput and minimize manual intervention. This integration boosts productivity while maintaining consistent quality. Such lines are used to produce fittings, valve bodies, plumbing parts, and industrial connectors, components where dimensional accuracy and surface quality are non-negotiable. Behind every forged brass part is a series of controlled high-temperature, high-force operations, each step calibrated to get the metal flowing in just the right way.